Look up at the night sky on a clear evening, and you'll see countless stars glittering in the dark. But there's one object that stands out, shining brighter and steadier than most. That's Jupiter, a world so immense it could swallow every other planet in our solar system and still have room to spare. For centuries, we've gazed at it with wonder, watched its dance among the constellations, and tried to decipher what lies behind that brilliant, placid glow. But what if I told you that Jupiter is far more than a beautiful sight? Beneath those serene, striped clouds swirls a storm of secrets so profound that even our most advanced probes have only begun to scratch the surface. Think about it. Here is a planet so massive its gravity shapes the entire solar system, deflecting comets, tugging at orbits, and acting as a silent guardian of the inner worlds. Yet for all its influence, Jupiter remains one of the greatest enigmas in modern astronomy. Its atmosphere is a canvas of violent beauty, painted with bands of ammonia clouds and punctuated by the Great Red Spot, a storm larger than Earth that has raged for centuries. But these are just the surface details. What's truly astonishing are the 25 jaw-dropping mysteries hiding within and around this gas giant phenomena that defy explanation and challenge everything we think we know about planetary science. So join me on a journey beyond the familiar, into the heart of a world that continues to astonish researchers and dreamers alike. We're about to explore the unknown, from powerful polar auroras that shouldn't exist to a magnetic field so strong it creates its own miniature cosmos, to the possibility of hidden oceans beneath miles of crushing gas. Each of these 25 mysteries pulls back another layer of Jupiter's story, reminding us that some of the universe's greatest wonders are waiting, right here in our own celestial backyard, daring us to look closer and ask bigger questions. First on our list of Jupiter's great enigmas is perhaps its most iconic, the Great Red Spot. This colossal, swirling storm is so vast that our entire planet could fit inside it, yet for centuries it has persisted as a tempest of almost unimaginable power. Think about the most violent hurricane ever recorded on Earth. Its fury measured in days, its energy eventually spent as it moves over land or cooler waters. Now consider a storm that has not merely lasted for weeks, but for hundreds of years, a maelstrom observed by astronomers since the invention of the telescope. The fundamental question isn't just how it formed, but how anything in nature can sustain itself for so long without fading away. Scientists classify the Great Red Spot as an anticyclone, a high-pressure storm where winds roar counter-clockwise at speeds exceeding 400 miles per hour. These winds are trapped between two powerful jet streams flowing in opposite directions, effectively sealing the storm in a perpetual state of fury. But this atmospheric cage alone doesn't solve the mystery of its endurance. On Earth, storms are powered by warmth from the ocean, but Jupiter has no ocean. It's a gaseous world. So what is the engine feeding this beast? One compelling theory points to the internal heat rising from Jupiter's core. This planet radiates more energy than it receives from the sun, and that tremendous upward surge of thermal energy may be the hidden power source that constantly reinvigorates the storm, preventing it from ever truly weakening. Yet even this ancient titan is not immune to change. Recent observations have confirmed the Great Red Spot is undergoing a profound transformation. It's shrinking. Measurements show it has narrowed significantly over the past century, becoming more circular than oval, and its intense red color has occasionally faded to a pale salmon hue. Some researchers suggest these changes might be part of a much longer, cyclical pattern of contraction and expansion we simply haven't observed before. Others wonder if we are witnessing the storm's gradual, final decay. This slow disappearance adds another layer of urgency to the mystery, compelling us to study it in detail before it potentially vanishes, taking its secrets with it. What we learn from its longevity and its possible death could rewrite our understanding of fluid dynamics and meteorology on a planetary scale. While the Great Red Spot represents a visible and atmospheric puzzle, our next mystery takes us deep into the heart of Jupiter itself, to a fundamental assumption that has been completely upended. For generations, the textbook image of a gas giant was simple: a massive, rocky core of heavy elements, acting as a seed around which an immense atmosphere of hydrogen and helium accumulated. This core was thought to be a distinct solid sphere, perhaps 10 to 20 times the mass of Earth. But data from the Juno spacecraft has utterly shattered that classic model, revealing instead that Jupiter's core is not a compact ball but something bafflingly diffuse, a fuzzy or diluted region that blends gradually into the surrounding metallic hydrogen ocean, challenging the very foundation of how we believe planets are built. This revelation came from Juno's exquisite measurements of Jupiter's gravity field. By precisely tracking the subtle tug of the planet's gravity on the spacecraft as it swooped close during its polar orbits, scientists could map the distribution of mass deep within the gas giant. They expected to find a clear, dense concentration of material at the center. Instead, the data painted a picture of a core that is partially dissolved or eroded, stretching across nearly half of Jupiter's radius. It's as if the planet's heart has been stirred into a murky broth of rock, ice, and metallic hydrogen, with no sharp boundary between where the core ends and the interior begins. This dilute core suggests the heavy elements are not neatly gathered in the center, but are mixed much higher up into the envelope, a finding that left planetary scientists scratching their heads. The existence of this fuzzy core is profoundly problematic for our models of planetary formation. The leading theory, known as core accretion, posits that our solar system began with a swirling protoplanetary disk of gas and dust. Dust grains clumped together to form pebbles, then rocks, then planetesimals, and eventually a massive rocky core that reached a critical threshold about 10 Earth masses. Once that milestone was achieved, its gravity became strong enough to rapidly pull in and hold onto the vast amounts of hydrogen and helium gas that make up Jupiter's breathtaking bulk. But if the core was never a compact, dense object to begin with, how did it ever reach that critical point of gravitational dominance? It creates a sort of planetary chicken and egg paradox that forces us to reconsider the entire sequence of events. One compelling hypothesis to resolve this paradox is that Jupiter's early, solid core was shattered by a cataclysmic impact with another protoplanet, a collision of unimaginable force that literally scattered the core's material throughout the inner region. Another, perhaps more elegant, theory suggests that the core may have never been truly solid in the first place. Instead, it could have formed through the gradual accretion of smaller planetary building blocks that were already mixed with gas as they descended, creating a diluted region from the very start. There's even a possibility that intense heat and pressure at Jupiter's center have gradually dissolved the core over billions of years, like a sugar cube stirring into a cup of hot tea over eons. Each of these ideas has major implications, not just for Jupiter, but for the thousands of gas giants we've discovered orbiting other stars. If our solar system's prime example of a gas giant doesn't play by the rules we wrote for it, how many other worlds out there have we completely misunderstood? This fuzzy core forces a rewrite of the cosmic recipe book, reminding us that the universe always has more surprises in store. But as we peer deeper into this magnetic phenomenon, the plot thickens with yet another puzzle. Earth's auroras are famously tied to the interaction of our magnetic field with particles from the solar wind, creating shimmering curtains of light near the poles. Jupiter's auroras, however, seem to operate on a completely different principle. The solar wind does play a role, but it's not the primary driver. Instead, the incredible energy appears to be generated from within the Jupiter system itself. The planet's rapid rotation, spinning once every 10 hours combined with the gravitational influences of its largest moons, particularly volcanic Io, creates a complex and self-sustaining particle accelerator of staggering proportions. Io, the most volcanically active body in our solar system, constantly spews vast amounts of sulfur and oxygen ions into space. Jupiter's immense magnetic field captures these particles, whipping them around at nearly light speed along flux tubes, invisible highways of magnetic force that connect the Moon to the planet's polar regions. This creates a vast, donut-shaped plasma torus around Jupiter, a ring of supercharged particles that feeds directly into the auroral engines. It's a closed circuit of cosmic power, where the planet's own rotation and its moon's eruptions provide the fuel, making these light shows partially independent of the sun's mood swings, a feature unseen on any other world we've studied. The most baffling aspect, however, is the rhythmic pulsing of the X-ray auroras. These aren't random flickers but steady, predictable beats occurring like clockwork every 27 to 45 minutes. It's as if a cosmic conductor is leading an invisible orchestra, triggering these immense bursts of energy with metronomic precision. Scientists suspect this pulsation might be tied to vibrations within Jupiter's magnetic field lines. As these lines become overloaded with particles from Io, they may snap and rebound, much like an overstretched elastic band, releasing their stored energy in a regular, explosive pulse that travels along the magnetic field and ignites the aurora. Yet the precise mechanism that sets this perfect tempo and why it remains so stable remains one of the most active and tantalizing areas of research at the gas giant. Just when we thought Jupiter's powerful magnetic field couldn't get any more bizarre, the Juno mission delivered its most head-scratching revelation yet. We're used to thinking of planetary magnetic fields as somewhat orderly things, like the field around Earth, which resembles a simple bar magnet with two clear, symmetrical poles north and south. Jupiter's field, by contrast, is a glorious mess. It's profoundly lumpy, uneven, and spectacularly chaotic. In one region, the magnetic force is incredibly intense. In another, just a short distance away, it's remarkably weak. This complete lack of symmetry defies nearly every conventional model scientists had for how these fields are generated, pointing to processes deep within the planet that are far stranger than we ever imagined. The most striking feature in this magnetic puzzle is a concentrated area of immense power near Jupiter's equator, a region scientists have nicknamed the Great Blue Spot. Unlike its famous atmospheric cousin, this isn't a swirling storm you can see. It's an intense, localized patch of magnetic energy, a kind of cosmic bruise on the planet's invisible field. Data from Juno shows the magnetic field here is exceptionally strong and concentrated, acting like a second, unofficial South Pole situated completely out of place. This single anomaly throws the entire classic dipolar model into disarray, forcing us to confront a simple but profound question. What could possibly create such a powerful and isolated magnetic knot in a part of the planet where, according to textbook physics, it just shouldn't exist? The answer likely lies in the exotic nature of Jupiter's interior. Planetary magnetic fields are generated by the churning motion of electrically conductive fluids deep inside a world, a process known as a dynamo. On Earth, that fluid is primarily molten iron swirling in the outer core. On Jupiter, the dynamo is believed to be driven by metallic hydrogen, a form of hydrogen under such immense pressure that it behaves like a liquid metal and can conduct electricity. But Juno's findings suggest this metallic hydrogen ocean isn't churning in a uniform, organized way. Instead, the dynamo action appears to be happening in separate, distinct layers or pockets, with the Great Blue Spot possibly representing a colossal upwelling or a turbulent jet of this conductive material that is breaking through from the deeper interior and punching into the outer layers. This incredible irregularity paints a picture of an interior that is far more complex and stratified than a simple ball of swirling hydrogen. Some scientists theorize that under the extreme pressures inside Jupiter, the hydrogen itself might be transitioning through different phases, from molecular to metallic, not in a smooth gradient but in a series of abrupt layers like a cosmic onion. The violent dynamics at the boundaries between these layers could be generating these wildly different and competing magnetic domains, creating a field that is essentially patched together from several different dynamos all operating at once, rather than from one unified global engine. The implications of this magnetic weirdness stretch far beyond Jupiter itself. It forces a fundamental rethinking of how gas giants and exoplanets throughout the galaxy might operate. For decades, we've modeled the magnetic fields of distant worlds based on our own solar system's assumptions. Jupiter is now telling us that those assumptions were far too simple. A planet's magnetic field is a direct window into its soul, revealing the hidden motions and structure of its deep interior. Jupiter's soul, it turns out, is not a placid, organized place, but a chaotic and deeply layered realm of competing forces, a truth that makes this giant world more fascinating and enigmatic than ever. If the chaotic and asymmetrical nature of Jupiter's magnetic field left us questioning our grasp of planetary interiors, our next mystery plunges us into an even more fundamental puzzle, one that strikes at the very heart of how our solar system was built. When the Galileo probe plunged into a seemingly average patch of Jupiter's atmosphere in 1995, scientists were poised to finally answer a critical question: just how much water is stored within this giant world? The leading theories were confident in their predictions. They suggested Jupiter should be incredibly water-rich, a wet world holding perhaps 2 to 3 times the amount of oxygen locked in water than the Sun contains. The actual data, however, delivered a result so baffling and dry that it sent planetary scientists back to the drawing board, completely rethinking the ingredients that went into making our largest planet. The reason for expecting so much water is tied directly to our model of the solar system's birth. We believe the planets formed from the same swirling cloud of gas and dust that created the Sun. In the cold, outer regions of this protoplanetary disk, beyond what's called the frost line, temperatures were low enough for water to condense into solid ice grains. These icy particles were abundant building blocks, meaning the planets that formed out there, the gas giants like Jupiter and Saturn, should have accreted enormous amounts of water ice. Jupiter, as the largest and first to form, was predicted to be the grand reservoir of this primordial water. Measuring its water abundance was seen as a direct way to test this entire formation scenario. The Galileo probe was sent to do just that, sampling the atmosphere's composition as it descended. The result was a profound shock. Instead of finding an atmosphere saturated with water vapor, the probe transmitted data indicating the region it sampled was startlingly, almost paradoxically, dry. The concentration of water was far lower than expected, not double or triple the solar abundance, but in some measurements it appeared to be only a fraction of it. It was as if you opened a giant container you believed was filled with water, only to find it mostly empty. This immediately created the water mystery. Had our theories about the solar system's formation been completely wrong? Or was there something strange about the specific location where the probe happened to land? This is where the plot thickens. The Galileo probe didn't descend into Jupiter at a random location. It targeted a specific area known as a hotspot, a region of unusually clear, dry atmosphere where we can see deeper into the planet. Scientists initially thought these were ideal spots to measure well-mixed global abundances. But what if these hotspots weren't representative of the whole planet? Subsequent observations from Earth-based telescopes and later from the Juno spacecraft revealed that Jupiter's atmosphere is not a uniform cocktail. It's a patchwork of extremes with massive weather systems that create vast, wet plumes of clouds adjacent to these dry, sinking air regions. The probe might have inadvertently plunged into a local desert, an atmospheric downdraft that had dried out, giving us a skewed, local measurement rather than a global average. More recent data from Juno's microwave radiometer supports this idea, suggesting that water may indeed be much more abundant near the equator, but its distribution is wildly uneven. churned and segregated by Jupiter's powerful weather. Yet, even with this new information, the initial mystery planted a seed of doubt that has grown into a much larger and more fascinating question. If Jupiter's water isn't evenly mixed, why? And what does that tell us about the planet's interior? Some scientists now propose that instead of being well mixed, Jupiter's heavier elements, including water, might have settled into layers or sunk toward the core, making the outer atmosphere deceptively poor in these compounds. The implications ripple outward, forcing us to reconsider not just Jupiter, but the entire narrative of planetary formation. Perhaps the early solar system's building blocks weren't as uniform as we thought. Maybe Jupiter migrated inward from a drier birthplace, or its immense gravity selectively accreted different materials. Each possibility challenges a different piece of the puzzle. This quest for water isn't just about one element. It's a search for the original recipe of our solar system, and Jupiter, it seems, is still keeping a crucial part of that recipe secret. While Jupiter's water mystery forced us to rethink the planet's formation, its atmosphere held another, entirely separate compositional puzzle involving a far more abundant compound, ammonia. This simple molecule, made of nitrogen and hydrogen, is a key ingredient in Jupiter's signature beige and white cloud decks. For decades, planetary scientists assumed that powerful storms and jet streams would keep this gas thoroughly mixed throughout the vast atmospheric layers, creating a relatively uniform distribution from the equator to the poles. But when the Juno spacecraft began mapping the planet's composition with its microwave radiometer, it revealed a pattern of ammonia so strange and unexpected that it completely overturned our understanding of how gases circulate on a world without a solid surface. The data Juno sent back showed that ammonia is not evenly distributed at all. Instead of a well-blended atmosphere, the readings painted a picture of dramatic highs and lows. Ammonia concentrations were surprisingly rich in the deep atmosphere near the equator, forming a wide, supercharged band around the planet's belly. But just a bit higher up, and especially toward the poles, the gas seemed to almost vanish, dropping to levels far lower than any model had predicted. This bizarre distribution created an immediate mystery. If turbulent weather is constantly churning the atmosphere, what powerful, hidden force is actively segregating this gas, pooling it in some regions and ruthlessly stripping it from others? The most compelling explanation points to a previously unimagined meteorological process. Scientists now believe that ammonia is being transported through the atmosphere not by broad, predictable weather patterns, but by incredibly narrow and intense upwellings, like thin, frenzied geysers of gas erupting from the deep interior. These ammonia-rich plumes punch their way up through the colder outer layers of the atmosphere. As they rise, the ammonia acts as an antifreeze within the updraft, preventing other gases from condensing and allowing the plume to maintain its momentum and identity all the way to the top. Once this enriched air reaches the cold upper atmosphere, it spreads out, rains down, and creates those localized pockets of high concentration that Juno detected. This process, however, is only half the story. For there to be such stark contrasts, there must also be corresponding downdrafts, areas where ammonia-poor air is sinking from the upper atmosphere back into the depths. This creates a kind of atmospheric segregation where the planet is effectively running a giant, invisible distillation system. The plumes carry moist, ammonia-rich air upward, while the surrounding drier air sinks, creating a patchwork of wet and dry columns side by side. This circulation is far more similar to the cell-like patterns we see in Earth's oceans than to any gas giant weather model we had before. What makes this discovery so revolutionary is that it reveals a hidden architecture within Jupiter's seemingly chaotic atmosphere. Beneath the riot of clouds and storms, there is an organized, if complex, system of circulation operating on a global scale. These narrow plumes are the planet's way of moving heat and material from its hot interior out into the frigid reaches of space. The missing ammonia wasn't actually missing. It was simply hiding in plain sight, organized by processes we were only able to see once we could look beneath the cloud tops. This finding doesn't just solve one mystery, it opens a new window into the energetic heart of a giant, showing us that even its most basic functions are still waiting to be fully understood. Just when we thought Jupiter had shown us all its atmospheric tricks, it presents us with a phenomenon that is both familiar and utterly alien: lightning. We see it flash in the darkness of a terrestrial storm, a sudden, brilliant discharge of electrical energy. Jupiter has lightning too, but as with so many things on this world, it operates by a completely different set of rules. The lightning there is not just a more powerful version of our own. It's a fundamentally different beast occurring in a different place for different reasons, and pointing to a distribution of heat and energy within the gas giant that we are only beginning to comprehend. The first major clue that something was off came from the Voyager missions, which detected the low-frequency radio waves, the telltale static crackle known as whistlers, that are the unmistakable signature of lightning. But the data was puzzling. The flashes seemed to be associated with the beautiful, swirling cloud tops we could see. Later missions, especially Galileo and Juno, revealed the stunning truth. While Earth's lightning originates in the water clouds relatively high in our atmosphere, Jupiter's lightning is born incredibly deep. The bolts we can detect erupt from layers where the atmospheric pressure is a crushing 5 to 10 times greater than Earth's sea level, a depth where water, not ammonia, is believed to form the clouds. This means the forces creating these electrical storms are operating in a hidden, high-pressure realm far beneath the visible surface, in conditions we can barely simulate. This leads to the second, and perhaps even more baffling, mystery of distribution. On our planet, lightning is a child of the equator. The tropics are Earth's furnace, where the strongest solar heating occurs, fueling the massive convection storms that generate electrical charge. It's a pattern driven directly by sunlight. Jupiter, however, flips this logic entirely on its head. The Juno spacecraft star camera, designed to help with navigation, became an accidental lightning detector, capturing thousands of brilliant flashes. But the vast majority of them were not clustered around the sunny equator. Instead, they were overwhelmingly concentrated near the planet's poles. This is the complete opposite of what solar-driven weather would predict, and suggests that Jupiter's internal engine, not external sunlight, is the primary power source for its most violent storms. So what is driving this polar tempest? The answer appears to lie in the planet's own internal heat. Jupiter radiates almost twice as much energy as it receives from the Sun, and this tremendous surplus has to escape somehow. At the equator, the planet's rapid rotation drives powerful zonal jets that likely stabilize the atmosphere, suppressing the large-scale upwelling needed to form megastorms. But at the poles, which are free from the dominating influence of these east-west jet streams, the heat from the deep interior can rise much more freely. This creates massive, turbulent convection cells, columns of warm gas rising, cooling, and falling, that churn the polar atmosphere with a violence unseen elsewhere. It is within these immense, churning columns that the conditions for lightning are perfectly met. Water and ice crystals carried high into the atmosphere collide, creating the separation of electrical charge that eventually discharges in a brilliant flash of light. This bizarre concentration tells a profound story about Jupiter's nature. It is a world powered from within, its weather systems governed not by the sun's gentle warmth, but by the ferocious heat bleeding from its own primordial heart. The poles act as release valves for this immense internal energy, making them the stormiest and most electrically active places on the planet. Understanding this helps us see Jupiter not as a passive orb reflecting sunlight, but as a dynamic, self-sustaining world with its own fierce and independent climate, a place where the weather is truly out of this world. We've just explored how Jupiter's internal heat fuels its bizarre polar lightning, but that immense energy doesn't just create flashes of light. it also powers some of the most breathtaking and mystifying weather patterns ever discovered. When the Juno spacecraft first swung over Jupiter's poles, it revealed a sight that no planetary scientist had ever predicted. Instead of a chaotic jumble of storms, the view was one of startling, almost artificial geometric perfection. At the North Pole, 8 colossal cyclones, each nearly as wide as the continental United States, were arranged with near-perfect symmetry around a single, massive central storm. At the South Pole, 5 equally immense cyclones performed the same precise dance around their own central vortex. These were not temporary features. They have remained locked in this stable, polygonal formation for years, defying every known law of fluid dynamics and atmospheric behavior. The immediate mystery is why these storms don't do what every cyclone on Earth eventually does: merge. On our planet, when 2 hurricanes get too close, they begin to orbit each other in a dance known as the Fujiwara effect, eventually either spinning apart or, more commonly, merging into a single, larger storm. It's the atmospheric equivalent of 2 droplets of water beating together. Jupiter's polar cyclones are clearly within each other's gravitational influence, yet they steadfastly refuse to combine. They maintain a fixed distance from their neighbors and the central storm, like planets orbiting a star or pieces on a fixed celestial clockwork. This bizarre stability suggests there are unseen forces at work, acting like invisible barriers that keep these titanic weather systems forever apart. One leading theory points to the presence of an antifreeze effect within the storms themselves. These cyclones are not just spinning masses of gas. They are likely wet convection storms, meaning they are powered by the rising and cooling of moist air. As the warm, ammonia and water-rich air from Jupiter's deep interior rises at the poles, it creates these immense rotating structures. The rising air within each cyclone may be surrounded by a ring of sinking, drier air, creating a kind of protective atmospheric moat around each storm. This ring of descending dry air could act as a buffer zone, preventing the spinning walls of the cyclones from ever actually touching, and thus eliminating any chance of them merging. It's as if each storm is encased in its own invisible defensive force field. But a defensive moat doesn't fully explain the precise geometric arrangement. Why 8 in a perfect octagon at one pole and 5 in a pentagon at the other? This is where the dynamics may get even more exotic. Some computer models suggest that the answer lies not in the storms themselves, but in the incredibly high-speed jet stream that likely whips around the pole, trapped by the planet's rapid rotation and powerful Coriolis force. This fast-moving river of air could be acting like a rotating fence, corralling the cyclones and holding them in their specific positions. The number of storms might be determined by the speed of this jet and the available space, creating a stable resonance where the storms find an equilibrium, forever chasing each other around the pole without ever catching up. The stability of this polygonal pattern offers a profound clue about the environment deep beneath the visible cloud tops. Their long-term persistence suggests that the polar atmosphere is far less turbulent at depth than we might have assumed. There appears to be a delicate and powerful balance between the energy welling up from below, which constantly feeds the storms, and the organized dynamics at the pole that contain them. This isn't a temporary accident, it's a permanent, engineered-like feature of Jupiter's climate, a natural masterpiece of balance that has likely persisted for decades, if not centuries. Unlocking the secret of why these storms don't merge doesn't just solve a Jovian puzzle. It gives us a new set of physical principles for understanding atmospheric stability on every gas giant we might discover in the cosmos. Now, having witnessed the stunning meteorological consequences of Jupiter's immense internal energy from the polar cyclones to the deep lightning, we are led to a more fundamental and pressing question: where does all this power actually come from? This brings us to our 9th great mystery, Jupiter's internal heat source. The numbers alone are staggering. While the giant planet receives a certain amount of warmth from the distant sun, it radiates back into space nearly twice that amount of energy. This means Jupiter is producing a tremendous surplus of heat from within its own core, a constant and prodigious output that has been warming its atmosphere and driving its storms for billions of years. For a world that was once thought to be a simple, cooling ball of gas, this persistent furnace at its heart is a profound enigma that challenges our most basic ideas about how planets evolve. The classic textbook explanation for this heat is a process known as the Kelvin-Helmholtz mechanism. The idea is elegantly simple. Jupiter is so massive that its own gravity is perpetually squeezing it, causing the entire planet to very slowly contract. Think of it like a bicycle pump. When you compress the air inside, the pump gets warmer. On a planetary scale, as gravity pulls Jupiter's vast bulk inward, the energy of that compression is converted into heat, which then slowly leaks out over eons. This process is real, and calculations show it could account for a significant portion of the heat we observe. But there's a major problem. The math doesn't quite add up. Based on models of planetary formation and cooling, a planet of Jupiter's age and size should have contracted enough by now that this mechanism would be winding down, producing far less heat than we actually measure. The observed heat flux is simply too high, suggesting that gravitational contraction alone cannot be the whole story. Something else, something more energetic, must be supplementing this planetary warming. This discrepancy has forced scientists to dig for deeper, more exotic explanations. One compelling theory involves the gradual descent of heavier elements through the planet's interior. Imagine Jupiter's atmosphere as an immense ocean of liquid metallic hydrogen. Within this ocean, denser materials like helium droplets or rocky metallic rain, precipitates formed under incredible pressure, could be slowly sinking toward the core. As these heavier fragments fall through the less dense liquid surrounding them, they release gravitational potential energy, effectively converting their slow-motion descent into pure heat. This process, akin to the inner workings of a star but on a planetary scale, could provide a powerful and long-lasting energy source that perfectly supplements the heat from gradual contraction, potentially solving the mystery of the surplus. Yet, even this elegant idea has recently encountered a major hurdle. Observations suggest that the abundance of neon in Jupiter's upper atmosphere is lower than expected. Why does that matter? Neon is what's known as a noble gas. It doesn't react chemically or dissolve easily. However, under the extreme conditions inside Jupiter, it's theorized that neon could actually dissolve into liquid helium, forming droplets that would then sink. If this helium rain is indeed happening, it would efficiently drag neon down into the deep interior, depleting it from the upper atmosphere we can observe. This sinking rain would also release a tremendous amount of gravitational energy, making it a prime suspect for the missing heat source. The observed neon depletion seems to support this theory, but the complex physics of materials under such extreme pressure means we still can't say for certain if this process generates enough energy to close the gap. The most speculative but fascinating theory pushes the boundaries of planetary physics into entirely new territory. Could there be processes occurring deep within Jupiter's core that resemble a form of nuclear fusion? In the crushing pressures at the planet's center, where hydrogen is squeezed into a metallic state, some scientists have proposed that unusual nuclear reactions might be possible. These wouldn't be the same as the fusion powering our sun, which requires immense temperatures, but rather a lower energy type catalyzed by the extreme pressure itself. It's a controversial idea, far from the mainstream, but it highlights the depth of the mystery. When conventional physics falls short, we are forced to consider possibilities that once seemed like pure science fiction. The truth is, we are likely looking at a combination of these processes. Jupiter's internal heat engine is probably powered by a symphony of mechanisms: the steady crush of gravity, the constant drizzle of helium rain, and the settling of heavier elements, all working in concert over billions of years. Pinpointing the exact contribution of each is the real challenge, and it's a challenge that matters far beyond our solar system. Jupiter is an archetype for the gas giants we see orbiting other stars. If we misunderstand how it generates its heat and evolves over time, we misunderstand the basic life cycle of a whole class of planets throughout the galaxy. This makes the mystery of its inner furnace not just a question about one world, but a key to unlocking the history and behavior of countless giants across the cosmos. After witnessing the immense internal forces churning within Jupiter, from its hidden heat source to its polar tempests, we now turn our gaze outward to a feature so subtle it was only confirmed in 1979 by the Voyager spacecraft, Jupiter's rings. Unlike the breathtaking, icy banners of Saturn that dominate the sky, Jupiter's rings are a ghostly, ethereal presence, a whisper of dust encircling the giant. This very subtlety is what makes them so profoundly mysterious. How can a planet with gravity so powerful it can tear comets apart simultaneously maintain a fragile, dusty halo that should, by all rights, be instantly dragged down into the clouds below? The existence and persistence of these rings defy simple logic, pointing to a delicate and continuous cosmic recycling process happening right under our noses. The first clue to this puzzle lies in the ring's starkly different composition. Saturn's glorious rings are primarily made of water ice, chunks ranging in size from tiny crystals to massive boulders, all reflecting sunlight brilliantly. Jupiter's rings, by contrast, are composed almost entirely of fine, dark dust particles, most no larger than the specks you might find on a dusty windowsill. This dust doesn't reflect light well. Instead, it scatters it, which is why the rings appear faint and are only visible when backlit by the sun, like seeing dust motes in a sunbeam. This fundamental difference in material immediately tells us that the formation process for Jupiter's rings is nothing like Saturn's. They are not the shattered remains of a large, icy moon that wandered too close and was torn apart by gravity. Their story is far more peculiar. The prevailing theory that solves both the origin and persistence of these rings involves a gruesome form of cosmic supply chain. Jupiter's powerful gravity doesn't just attract, it acts as a relentless source of impacting projectiles. Small asteroids and cometary fragments are constantly being pulled toward the planet at tremendous speeds. When these objects cross the orbits of Jupiter's four small inner moons, Metis, Adrastea, Amalthea, and Thebe, they don't just sail past, they slam into the surfaces of these moons with catastrophic force. These hypervelocity impacts are so violent that they blast clouds of fine dust and debris directly off the moon's surfaces, launching the material into space to join the ring system. In this light, the rings are not a static structure but a dynamic, ever-changing cloud of ejecta, a permanent dust storm generated by perpetual celestial bombardment. This explains the rings' existence, but a deeper mystery remains: their structure and stability. Why doesn't this dust simply float away or fall into Jupiter? The answer reveals an elegant orbital dance. The four source moons orbit within and adjacent to the ring system itself. As they travel around Jupiter, their gravity shepherds the dust particles, acting like celestial sheepdogs that corral the debris into specific, organized bands. The main ring is confined by the moon's Metis and Adrastea. Even more fascinating are the two faintest components, the gossamer rings. These incredibly diffuse, pancake-thin rings are directly associated with the moon's Amalthea and Thebe. The dust blasted from these moons is pulled into orbits that precisely mirror their parents, creating a ring that extends from the moon's orbit inward toward Jupiter. The entire ring system, therefore, is not a random cloud but a meticulously organized map of its source moon's gravitational influence. Yet even this elegant system has an expiration date. Individual dust particles, constantly buffeted by Jupiter's powerful magnetic field and slowed by the thin plasma that surrounds the planet, should gradually lose energy and spiral inward on a timescale of just decades to a few centuries, eventually burning up in the upper atmosphere. The fact that we still see the rings today means this entire process, the impacts, the ejection, the shepherding, is not a one-time event from the distant past. It is happening constantly right now. The rings we see are in a perfect state of equilibrium, a celestial balancing act where new dust is being added from the moons at the same rate that old dust is spiraling down to its doom. Jupiter's rings are less a permanent monument and more a fleeting, shimmering phenomenon, like a waterfall that maintains its shape not because it's frozen, but because the water is always moving. This endless cycle of creation and destruction, governed by the orbits of a few small moons, paints a picture of a dynamic system that is both violent and beautiful, a stark reminder that even the most subtle features in our solar system can hold some of its most compelling secrets. Just as Jupiter's faint rings reveal a system of delicate balance, our next mystery plunges us into a realm of pure, terrifying power. Surrounding the planet is a donut-shaped zone of energy so ferocious that it holds the title for the most hazardous environment in our entire solar system, Jupiter's radiation belt. This is not a gentle halo of light, it's a punishing torrent of atomic shrapnel, a particle accelerator of cosmic proportions where electrons are whipped to nearly the speed of light. The sheer intensity of this radiation is so far beyond anything near Earth that it presents both a profound scientific puzzle and a monumental engineering nightmare for any spacecraft daring to get too close. To grasp the sheer scale of this phenomenon, it helps to compare it to Earth's own Van Allen radiation belts. Our planet's magnetic field traps charged particles from the solar wind, creating regions that can pose a risk to satellites and astronauts. But Jupiter's version is on an entirely different level. The energy of the particles trapped in Jupiter's grasp is thousands of times greater, and the radiation levels are so high that an unshielded human would receive a lethal dose in a matter of minutes. This extreme environment is a direct product of Jupiter's immense magnetic field, the strongest of any planet in our solar system, which acts like a giant, invisible magnet snagging charged particles and whipping them around at unimaginable velocities. The central mystery, however, isn't just that the radiation exists, it's the baffling mechanism that accelerates these particles to such insane speeds. We understand the basic principle: charged particles spiral along magnetic field lines, gaining energy as they go, but Jupiter's system is too efficient. The process is akin to pushing a child on a swing. A gentle, timed push can make the swing go very high. At Jupiter, something is giving these particles a series of perfectly timed, colossal pushes, accelerating them to relativistic velocities a significant fraction of the speed of light. The puzzle for scientists has been identifying the cosmic hand that's doing the pushing. What natural force can possibly be this powerful and this precise? Data from the Juno mission, which was specially hardened with a titanium vault to survive its polar plunge through the worst of these belts, has provided some tantalizing clues. The answer may lie in a two-stage process deep within the magnetosphere. First, the particles likely get an initial kick of energy from the chaos of the magnetic field itself. As we discussed earlier, Jupiter's field is anything but orderly. It's lumpy, asymmetric, and filled with turbulence. This chaos can inject energy into particles, much like a boat being tossed about in a stormy sea. But this initial kick isn't enough to explain the final, extreme velocities. For that, scientists are looking toward the planet's incredible rotation. Jupiter spins on its axis once every 10 hours, and this rapid spin may be the ultimate power source. The theory suggests that as the planet's magnetic field rotates, it gets twisted and stretched. The field lines near the planet are locked to its rotation and move fast, while the lines farther out in the magnetosphere are loaded down with plasma from Io and lag behind. This creates an enormous tension, like winding up a rubber band. Eventually, this stored energy must be released. Scientists believe it does so through a process called magnetic reconnection, where these tangled field lines suddenly snap and reconfigure into a new, more stable shape. The energy released in this snapping event is titanic, and it is this explosive process that may provide the final, devastating push, launching electrons on a runaway acceleration to near light speed. Yet, even this elegant explanation hits a snag. The radiation environment measured by Juno was even more intense than the most pessimistic models had predicted. There appears to be an additional, unknown factor supercharging the belts beyond what our current physics can account for. Some researchers speculate that the continuous and massive supply of particles from Eo's volcanoes creates a denser plasma environment than expected, which could facilitate more efficient energy transfer. Others wonder if there are additional, undiscovered acceleration zones or resonances within the complex magnetic field that we simply haven't mapped yet. This discrepancy between prediction and reality is a humbling reminder that Jupiter's ferocious heart still operates by rules we have not yet fully deciphered. This isn't just an academic exercise. Understanding this particle acceleration is crucial for the future of exploration. The radiation is so intense that it literally chews through spacecraft electronics, degrading solar panels and threatening onboard computers. The Galileo probe's eventual failure was hastened by the cumulative radiation damage it endured. Juno's orbit was carefully designed to avoid the most severe regions, dancing between the radiation belts and the planet itself to prolong its life. Every mission to the Jovian system must be designed around this invisible, deadly barrier. Unlocking the secrets of how this natural particle accelerator works is therefore essential not only for understanding the fundamental physics of our universe, but also for one day safely sending more advanced missions to study Jupiter's enigmatic moons, which orbit within this dangerous but fascinating realm. If the radiation belts showcase the terrifying power of Jupiter's magnetic environment, the planet's most visually stunning feature presents a mystery of breathtaking scale and persistence. When you picture Jupiter, you undoubtedly see its iconic banded appearance, those sweeping stripes of cream, ochre, tan, and blue that wrap around the planet in parallel lines. These bands are not merely a painted-on facade. They are the visible tops of the fastest, deepest, and most stable weather system in the solar system, driven by colossal rivers of wind known as jet streams. And at the heart of this beautiful chaos lies a fundamental puzzle that has challenged planetary scientists for decades. How do these alternating jets, particularly the powerful ones at the equator, maintain their perfect, unwavering structure against all the forces that should tear them apart? The basic mechanics of these jets are both simple and astounding. They are high-speed winds that blow eastward or westward, confined to specific latitudes and creating the boundaries between the planet's light zones and dark belts. The equatorial jet is especially monstrous, racing eastward at speeds around 350 miles per hour, vastly outpacing any hurricane-force wind on Earth. What's truly baffling is their incredible stability. Earth's jet streams meander, shift, and change with the seasons. Jupiter's jets, by stark contrast, have remained locked in the same positions at the same speeds for as long as we have been able to observe them with any detail. They are a permanent, unmoving feature on a world otherwise defined by violent and chaotic weather, acting like rigid, atmospheric skeleton holding the entire climate system together. This incredible permanence is the core of the mystery. In any fluid system, friction and other dissipative forces should slowly rob the flow of its energy, causing the winds to gradually slow down and eventually stop. On Earth, our weather is powered by the sun, with solar heating constantly adding new energy to the system to keep the atmosphere in motion. But Jupiter's weather occurs too deep in its atmosphere for solar energy to be the primary driver. Furthermore, the sheer power and stability of these jets suggest an energy source that is not only immense but also incredibly consistent and deep-seated. The sun's variable output simply cannot account for such unwavering force. the engine for this system must come from within the planet itself. This is where the classic model, which stood for decades, enters the picture. Scientists long believed these jets were primarily shallow weather phenomena, much like Earth's own jet streams. The theory was that the sunlight absorbed at the cloud tops created convection currents, columns of warmer gas rising and cooler gas falling. The planet's incredibly rapid rotation, a spin once every 10 hours, would then shear these rising and falling columns of air, twisting them into the east-west flows we observe as the banded jets. It was an elegant idea that used well-understood physics, but it had one major flaw. It predicted the jets would be a relatively superficial feature, perhaps only extending a few dozen miles beneath the visible cloud tops. The Juno spacecraft's gravity and microwave measurements completely obliterated this shallow weather hypothesis. The data revealed something far more profound and unexpected. These jet streams are not skin-deep. They are like the visible tips of planetary-scale icebergs, plunging astonishingly deep into the interior, perhaps as far as 1,800 miles down. This stunning depth means the jets are not a surface-level weather pattern, but are intrinsically linked to the massive bulk of the planet's interior, a fundamental part of Jupiter's very structure. Their roots tap into the same vast energy reservoir that powers its internal heat and its monstrous magnetic field. This revelation forces a dramatic rethink of what drives the jets. A shallow process like solar heating cannot possibly influence the atmosphere 1,000 miles down. Instead, the driving force must be the planet's own internal heat, which is rising from the deep interior and powering convection on a truly gargantuan scale. As this heat rises through the deep atmosphere, it likely encounters layers where the physical properties of hydrogen change dramatically, most notably at the boundary where molecular hydrogen transitions into liquid metallic hydrogen. The dynamics at this boundary could be the true engine room, generating turbulence that gets organized by Jupiter's rapid rotation into the coherent, deep jets we observe. Yet, even with this deep internal driver, the mystery of their stability persists. Why don't these deep flows eventually become turbulent and break down? The answer may lie in the unique properties of the fluid itself at those incredible depths. As hydrogen is compressed by immense pressure, it becomes a supercritical fluid, a state of matter that is neither a true liquid nor a gas, but has properties of both. This exotic fluid may behave in ways that suppress small-scale turbulence, allowing the larger, organized flow of the jets to dominate and persist for centuries. It's possible that the entire mass of the planet, spinning as a cohesive unit, acts as a flywheel that imparts its rotational energy to the atmosphere, keeping these colossal rivers of air flowing in a perfectly steady state. The bands we see from space, therefore, are not just winds, they are the surface expression of the planet's deep, churning heart, a visible testament to processes operating in a realm of pressure and heat we are only beginning to comprehend. Just as the incredible depth of Jupiter's jet streams revealed a planet fundamentally structured from the inside out, this churning interior manifests in another, far more visible way, the planet's ever-shifting palette. If you've ever looked at a series of Jupiter images taken over several years, you might notice something strange. The planet's iconic face seems to be slowly changing. Those crisp, contrasting bands of cream and brown aren't permanent. In a dramatic celestial makeover that unfolds over years, bright white zones can suddenly darken to a deep reddish brown, while dark belts can fade to a pale ochre or even brilliant white. This isn't a trick of the light, it's a real planetary scale transformation, and the trigger for these stunning color changes remains one of Jupiter's most visually captivating mysteries. At the heart of this puzzle is a fundamental difference between what we see and what's actually there. The creamy white zones are regions of rising air where upwelling ammonia gas freezes into bright, reflective ice crystals that form towering cloud decks. The darker brownish belts, by contrast, are areas where air is sinking, clearing away the high, bright ammonia clouds and allowing us to see deeper into the atmosphere. The coloration we perceive in these deeper layers is believed to come from a mysterious group of compounds that scientists call chromophores. These are complex molecules that absorb certain wavelengths of light, giving the regions their distinctive tan, brown, and reddish hues. The great color change mystery, therefore, boils down to a simple question: what causes these chromophores to suddenly appear, vanish, or change concentration across vast swaths of the planet? For a long time, the prevailing theory pointed a finger at chemistry driven by ultraviolet sunlight. The idea was that simple chemicals like ammonia and hydrogen sulfide, stirred up from the deep atmosphere, would rise to the upper cloud layers. Once there, they would be exposed to the sun's UV rays, which would provide the energy needed to catalyze complex chemical reactions, slowly cooking these simple ingredients into the darker, more complex chromophores. This would explain why the darker material appears in the belts, where the air is sinking and the cloud cover is thinner, allowing more sunlight to penetrate and fuel these photochemical reactions. The zones with their thick, reflective cloud tops would be shielded from this process, remaining bright white. It was an elegant, sun-powered explanation. However, this neat solar-powered model has begun to crack under closer scrutiny. The biggest problem is the timescale. These chemical reactions, relying on the relatively weak energy of sunlight, would be a slow, gradual process. But the observed color changes on Jupiter don't always happen gradually. Sometimes an entire belt can darken or lighten remarkably quickly over just a few Earth years. This speed suggests a much more powerful and dynamic engine is at work than mere sunlight. The focus has now shifted from the top down to the bottom up, with scientists suspecting the real trigger lies deep within the same interior heat engine that powers the jets and the storms. The new leading hypothesis is that these color changes are intrinsically linked to powerful planetary scale waves that move energy and material through the atmosphere. Specifically, scientists are investigating the role of giant convection cells, the same kind that fuel the polar cyclones, but acting on a global scale. Imagine a massive plume of warm, moist air, rich with those potential chromophore ingredients erupting from the deep, hot interior. As this plume surges upward through the atmosphere, it could act like a fire hose, injecting a concentrated burst of these darkening compounds directly into the upper cloud decks. This wouldn't be a slow, sun-cooked process. It would be a sudden, violent delivery from below, instantly altering the chemistry and appearance of a huge atmospheric region. This deep convection model elegantly explains several puzzling aspects. It accounts for the rapid pace of the changes, as these plumes can move immense volumes of material quickly. It also explains why adjacent bands can behave so differently. A powerful upwelling in one latitude could be busily creating a bright zone by pushing ammonia ice high into the sky, while a sinking region right next to it is simultaneously darkening as it pulls the darker compounds up into view. The entire Jovian atmosphere, in this view, is a constant three-dimensional battle between rising and falling columns of air, and the color we see is simply the scoreboard showing which process is currently winning in any given region. Yet, the mystery is far from solved. We still don't know the exact chemical identity of the primary chromophores. Candidates range from complex compounds of phosphorus and sulfur to broken down and reassembled molecules of ammonia itself, perhaps even involving organic molecules akin to those found in crude oil on Earth. Furthermore, the specific cue that prompts a Chinese letter region to suddenly erupt with one of these transformative plumes remains completely unknown. Is it a periodic release of built-up internal heat? Is it triggered by interactions between the deep jet streams? Or could it even be influenced by the gravitational tug of other planets in a long-term cycle we haven't yet detected? Each major color shift on Jupiter is a broadcast from its hidden depths, a message written in a chemical language we are still struggling to translate, telling the story of a world whose heart beats to a rhythm we are only beginning to hear. As we marvel at the dynamic color changes playing out across Jupiter's cloud tops, we are inevitably drawn to a question that strikes at the very nature of the planet itself. Where does the atmosphere end and the planet begin? On Earth, the answer is simple. The atmosphere is a thin, gaseous envelope resting upon a solid, rocky surface. But Jupiter, a gas giant, has no such surface to stand on, at least not in any familiar sense. This leads us to our 14th great mystery, the sheer, unfathomable depth of its atmosphere. We are not merely trying to measure the height of its clouds, we are attempting to plumb the bottom of a global ocean of gas, to find the hidden boundary where the familiar rules of weather give way to the exotic physics of a planetary interior. For decades, the prevailing view was that Jupiter's spectacular, banded weather layer was just that, a layer, a relatively shallow skin of churning clouds and storms, perhaps a few hundred miles deep, sitting atop a much calmer and denser interior. This model made intuitive sense. It allowed scientists to treat the visible atmosphere as a separate system, like the waves on the surface of an ocean, driven primarily by the energy of the sun. The true, deep interior could then be modeled as a more or less uniform, steadily rotating ball of fluid. It was a clean, manageable separation of processes. But as with so many of our assumptions about Jupiter, this neat divide has been completely upended by data from the Juno mission, revealing a reality that is far more complex and integrated. The key evidence challenging the shallow weather model came from Juno's precise measurements of Jupiter's gravity field. By tracking the subtle wobbles in the spacecraft's orbit, scientists could map the distribution of mass deep within the planet. If the winds were merely a superficial phenomenon, their motion would not contribute significantly to the gravity field. The data, however, told a different story entirely. The tremendous mass of the east-west jet streams, the very engines of the banded structure, creates a measurable gravitational signal. To have such a pronounced effect, these flows cannot be skin-deep. They must extend thousands of miles downward, representing a significant fraction of the planet's total mass in motion. This suggests the weather layer isn't a thin film but a profound abyss, a crushing ocean of hydrogen and helium that extends perhaps a staggering 10 to 15% of the way toward the planet's center. This revelation transforms our image of Jupiter from a world with a gaseous atmosphere to a world that is almost entirely atmosphere, a vast fluid sphere with no distinct surface. Imagine descending through those colorful cloud tops. You would pass through layers of ammonia ice, then ammonium hydrosulfide, and finally into a region of water clouds. But the descent wouldn't end there. For thousands of miles, the pressure and temperature would steadily increase, turning the gaseous hydrogen into a hot, dense fluid. Around 4,500 miles down, the pressure reaches about 2 million times Earth's atmospheric pressure. Here, something magical and bizarre happens. The hydrogen undergoes a phase transition into liquid metallic hydrogen. This is not a liquid like water. It is a quantum fluid that behaves like a liquid metal capable of conducting electricity. This is the source of Jupiter's monstrous magnetic field. The mystery of the atmosphere's depth is therefore inextricably linked to the mystery of this transition. Where exactly does it occur? Is it a sharp boundary like the surface of an ocean, or is it a gradual foggy gradient over hundreds of miles? The answer is crucial because this boundary is likely the engine room for the entire planet. The dynamics here, the churning of the metallic hydrogen dynamo and the convection from the deep interior, are what probably drive the deep jets we observe at the surface. The weather we see is not a separate system. It is the surface expression of these deep internal convulsions. Yet some conflicting evidence keeps the mystery alive. While the gravity data argues for deep winds, other observations, such as the behavior of certain cloud features and the planet's heat distribution, can still be interpreted through a shallower lens. Some models suggest that while the jets themselves are deep-rooted, the most vibrant cloud-level weather and color changes might be confined to a relatively thinner layer at the very top. It's possible we are looking at a system with multiple tiers of circulation, massive, slow-moving deep currents that set the stage, and more rapid, complex weather patterns playing out in the upper atmosphere like froth on the surface of a deep and powerful wave. Pinpointing the true depth of this atmospheric abyss is about more than just setting a new record. It is fundamental to understanding how gas giants are built, how they evolve, and how they work. It defines the very nature of the planet. If the winds extend thousands of miles down, it means the internal structure of Jupiter is not layered like a simple onion, but is thoroughly mixed and churned by these powerful flows, which would efficiently distribute heat and chemical elements from the core outward. This has dramatic implications for everything we think we know, from the nature of its fuzzy core to the distribution of its water. Each new piece of data pulls back another veil on this profound mystery, revealing a world that is not a ball with an atmosphere, but a living, breathing entity whose atmosphere is its entire being. But to truly understand the scale of this puzzle, we must first grasp how scientists use microwaves to see inside Jupiter. It's a bit like medical imaging for a planet. Different wavelengths of microwave radiation can penetrate the atmosphere to different depths before being absorbed or scattered back into space. Shorter wavelengths probe only the cold upper cloud decks, while longer wavelengths can delve hundreds of miles down into the warmer, denser atmospheric layers. By meticulously measuring the intensity of the microwaves coming out at each wavelength, researchers can essentially take the planet's temperature at various depths, building a vertical profile of its heat distribution and composition from the cloud tops down into the abyss. This data should paint a smooth, consistent, and predictable picture of a gradually warming atmosphere. The reality, however, is a chart of baffling contradictions. The longest wavelengths, which probe the deepest, return readings that are far warmer than any model predicts. It's as if you were taking the temperature of a lake by putting thermometers at different depths. You'd expect it to get steadily colder as you go toward the surface, but instead, your deepest thermometer shows a bizarre and intense heat spike that defies all logic. This suggests that something powerful and unexpected is happening in Jupiter's deep atmosphere, generating excess microwave emission that our current physical models simply cannot account for. The leading suspect is ammonia, a gas that is highly effective at absorbing and re-emitting microwave radiation. The anomalous heat signature could be caused by a dramatic and previously unknown unevenness in the distribution of this gas. One compelling theory is that Jupiter's powerful thunderstorms, which we know from our look at its lightning are far more intense than Earth's, are creating what scientists call mushballs. These are not soft, snowy objects but massive slush balls of ammonia and water that form in the high atmosphere during these colossal storms. These heavy mushballs would then plummet like hailstones the size of cars, rapidly transporting ammonia deep down into the atmosphere in narrow, concentrated columns. This would create those pockets of unusually high ammonia concentration that Juno detected, which would in turn emit the excess microwaves that are throwing off our measurements. It's a process that effectively robs ammonia from the upper atmosphere to hide it in the lower atmosphere, a chaotic, storm-driven redistribution that our serene, layered models never anticipated. However, the mushball theory, while elegant, may not be the complete answer. The microwave data is so strange that some researchers are questioning whether we even understand the fundamental physics of how microwaves interact with planetary atmospheres under such extreme conditions. The pressure and temperature thousands of miles below Jupiter's clouds create an environment where gases behave in ways we cannot replicate in any laboratory on Earth. It's possible that the absorption properties of ammonia itself are different under these incredible pressures, meaning our basic toolkit for interpreting the data could be flawed. The mystery of the microwaves, therefore, is not just a puzzle about weather. It's a potential signpost pointing toward entirely new physics, waiting to be discovered in the deep, churning heart of a giant. As we probe the depths of Jupiter's churning atmosphere and its enigmatic microwave emissions, our exploration now pulls us outward to the intricate family of worlds that orbit the giant. With nearly 100 known moons, the Jovian system is a miniature solar system in its own right, featuring an astonishing diversity of captured asteroids, shattered fragments, and 4 massive, planet-like Galilean moons. Yet within this vast celestial collection, a glaring and puzzling gap emerges, a cosmic missing link in the moon family tree. Why are there no intermediate-sized moons, nothing to bridge the dramatic gulf between the 4 giant Galilean satellites and the countless swarms of tiny, irregular moons? This absence isn't just a curious footnote, it's a profound clue to a violent and dramatic chapter in the solar system's early history, a story of cataclysmic collisions and ruthless gravitational editing. To appreciate the strangeness of this gap, we need to look at the moons themselves. On one end of the spectrum, we have the Galilean moons, Io, Europa, Ganymede, and Callisto. These are true worlds. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury, with its own subsurface ocean and a weak magnetic field. Callisto is nearly as large. Europa hides a global ocean beneath its icy crust, and Io is a volcanic hellscape. They are massive, spherical, and complex. On the other end, we have a menagerie of dozens of smaller moons, most only a few miles across. These are largely captured asteroids or the shattered remains of larger bodies, irregular in shape and often following wild, tilted orbits. The puzzling void lies squarely between them. There are no moons with diameters of, say, several hundred miles, nothing that would represent a mid-sized stepping stone between the planetary behemoths and the small rocky debris. This clear bifurcation in the size distribution is a pattern that demands an explanation, and it points toward a formative process that was anything but gentle. The most widely accepted theory to explain this missing middle class of moons is a period of absolute carnage in the early Jovian system, a celestial demolition derby driven by the immense gravitational pull of the growing planet. The leading model of moon formation suggests that Jupiter's largest moons, the Galilean 4, formed in a circumplanetary disk, a swirling ring of gas and dust that surrounded the infant planet, much like the protoplanetary disk that surrounded the young sun. Within this disk, dust grains would have clumped together to form moonlets, which then collided and merged in a process similar to how planets themselves formed. This would have created a whole population of growing protomoons of various sizes, but this is where the violence begins. The gravitational environment around a young Jupiter would have been intensely chaotic. The planet's gravity would have constantly perturbed the orbits of these dozens or even hundreds of growing moonlets. Their paths would have crossed, their orbits would have decayed, and catastrophic collisions would have been inevitable. Computer simulations of this era show that it wasn't a peaceful process of accretion. Instead, it was a series of high-speed, destructive impacts. Most of these moonlets would not have merged to grow larger. They would have shattered each other into countless smaller fragments. This relentless grinding down of the mid-sized population would have left behind only the 4 largest survivors, the Galilean moons, which had grown massive enough to withstand the bombardment, and a vast cloud of small debris representing the shattered remains of everything else. The missing intermediate moons, therefore, aren't missing at all. They were simply obliterated, their material either ejected from the system, absorbed by the larger moons, or ground down into the tiny irregular moons we see today. An alternative, but not mutually exclusive, theory involves the role of orbital migration. The Galilean moons, particularly the inner ones, are thought to have migrated outward from Jupiter over time due to gravitational interactions with the planet's circumplanetary disk. As they moved, their changing orbits could have acted like gravitational snowplows, clearing out a wide swath of space around them. Any intermediate-sized moons that had managed to form in these orbital corridors would have been gravitationally ejected from the system or hurled into collision courses with their larger siblings. This process would have efficiently scrubbed the inner and middle regions of the Jovian system of all but the most massive objects, further reinforcing the stark divide between the giants and the dwarfs. This peculiar size distribution isn't just a quirk of our own solar system. It may be a universal signature of giant planet formation. When we look at the moon systems of Saturn, Uranus, and Neptune, we see hints of a similar pattern, though often not as extreme. Each has a few major moons and then a sharp drop-off to numerous smaller ones. This suggests that the violent processes that shaped Jupiter's family, the collisional grinding and gravitational clearing, are fundamental to how giant planets assemble their entourages. The gap in moon sizes is a fossilized record of that early chaos, a lasting imprint of the ruthless dynamics that decide which worlds survive and which are consigned to dust. By solving the mystery of the missing middle, we don't just learn about Jupiter, we uncover a fundamental rule in the cosmic playbook of how planetary systems are built. Jupiter's family of moons holds worlds of stunning contrast, from the icy, potentially life-bearing ocean of Europa to the ancient, cratered face of Callisto. But no moon in the entire solar system is as violently alive as Io. If you could stand on its surface, you would witness a true vision of hell, a landscape constantly remade by fire, where volcanoes erupt not with mere smoke and ash, but with fountains of molten rock that can shoot dozens of miles into the black sky, and vast lakes of incandescent lava glow with temperatures hotter than any found naturally on Earth. Io is, by a staggering margin, the most volcanically active body we have ever discovered. The sheer intensity of its geological fury presents a fascinating puzzle. We understand the basic engine that powers it, but the reality of its output so wildly exceeds our predictions that it forces us to question whether we truly grasp the forces at work deep within this tortured world. The primary engine driving Io's inferno is not internal radioactive decay, as it is for Earth, but an external and incredibly powerful force, tidal heating. This process is a spectacular celestial tug-of-war. Io orbits Jupiter in a slightly elliptical or oval-shaped path, and it is not alone in its journey. Its orbits are locked in a precise gravitational resonance with the neighboring moons Europa and Ganymede. For every one orbit Ganymede completes, Europa completes 2 and Io completes 4. This perfect rhythm means the moons constantly tug on each other, preventing Io from settling into a perfectly circular orbit. As a result, its distance from Jupiter constantly changes. This varying distance is the key to the heating. Jupiter's immense gravity pulls much more strongly on the side of Io facing the planet than on the side facing away. As the moon moves along its elliptical path, the strength and direction of this gravitational pull flex and distort Io's very structure. Imagine repeatedly squeezing a soft rubber ball in your hand. The friction from that constant deformation generates heat. On a planetary scale, this is what happens to Io. Its entire interior is being kneaded by Jupiter's gravity, generating colossal frictional heat that melts its rock into vast global magma oceans. This much we understand. The models built on this principle predicted a volcanically active moon. What they did not predict was the apocalyptic level of activity we actually observe. The disparity between prediction and reality is striking. Based on the calculated tidal forces, scientists expected a total heat flow from Io's interior equivalent to about 1.5 terawatts, already an immense amount of energy. But measurements from spacecraft like Voyager, Galileo, and Juno reveal the actual value is more than double that, perhaps as high as 3.5 terawatts. To put that in perspective, this tiny moon, roughly the size of our own, releases more than 30 times the heat flux of the entire Earth, with all its volcanoes and tectonic activity. This leaves us with a fundamental mystery. If our understanding of tidal heating is correct, why is Io producing so much extra energy? What is the missing ingredient in our models that accounts for this shocking surplus? One compelling theory suggests the answer lies not in the present but in Io's past. The Moon's orbit may not have always been as fixed in its current resonance. It's possible that in the earlier history of the solar system, Io's orbit was even more eccentric or oval-shaped than it is today. A more elongated orbit would have subjected the Moon to far greater tidal flexing, generating significantly more heat. While the orbit has since circularized somewhat due to this intense energy dissipation, the interior might still be super hot from this ancient, more violent period, like a baked potato that remains hot long after being taken out of the oven. We could simply be witnessing the slow and spectacular cooling of a world that was once heated to an even more extreme degree. Another fascinating possibility involves the very structure of Io's interior. Our models often treat the Moon as a relatively uniform ball of rock. But what if it is far more complex? Some planetary scientists propose that the tidal heat is not generated evenly throughout Io's mantle. Instead, it could be focused in specific, incredibly hot layers or pockets. A partially molten mantle with a specific viscosity and composition could churn in a way that maximizes tidal friction in certain zones, creating localized furnaces of melt that boost the overall heat output far beyond what a simple, uniform model would predict. The magma itself might play a role in how the energy is transported to the surface, efficiently venting the incredible internal heat through countless volcanoes and fissures. The most intriguing missing factor, however, might be the role of Jupiter's own magnetic field. Io is immersed in this ferocious radiation belt, and a powerful electric current, known as the Io flux tube, streams between the Moon and the planet's poles. It's possible that these electrical currents are actually inducing additional heating within Io's interior, particularly in its potentially conductive magma oceans. This would add a second external heating mechanism on top of the tidal flexing, a double whammy of energy input that our models have only begun to tentatively explore. Unraveling this mystery requires us to see Io not as an isolated world, but as an integral part of a dynamic and electrified Jovian system, where the planet's influence extends far beyond gravity alone. Each tremendous eruption on Io is therefore a signal from the deep, a message in lava and plasma about the hidden workings of forces that connect a moon to its giant parent in ways we are still striving to fully comprehend. While Io represents a world of fire and brimstone, its neighboring moon Europa presents a vision of an entirely different extreme, a global, ice-covered ocean that has captivated scientists and dreamers alike as one of the most promising places to search for life beyond Earth. Hidden beneath a crust of ice perhaps 10 to 15 miles thick lies a body of liquid water so vast it contains more than twice the volume of all Earth's oceans combined. This alone is a stunning concept, but the deeper mystery lies in what exactly is dissolved in that dark, alien sea. What is the chemistry of this buried ocean? Is it a bitter, sterile brine, or could it hold a surprising cocktail of elements that would make it not just habitable, but already inhabited? The first clue that Europa's ocean might be more than just water comes from the Moon's fractured and stained surface. From afar, Europa looks like a cracked marble, crisscrossed with dark, rusty-looking streaks and ridges. Spectroscopic analysis reveals that these brownish stains are not just dirty ice. They are rich in salts, specifically magnesium sulfate, essentially Epsom salt, and likely sodium chloride, common table salt. These salts don't originate from the ice itself. They are a crucial piece of evidence pointing to a dynamic process. Scientists believe they are the evaporated remains of ocean water that has welled up from below through cracks and fissures, freezing on the surface and leaving its mineral content behind. This suggests the hidden ocean is not pure water, but a salty solution, much like our own seas. But where does this salt come from? On Earth, ocean salts largely come from the weathering of rocks on land. Europa has no land. The leading theory points to the moon's seafloor. Europa is believed to have a rocky mantle and a metallic core. The bottom of its global ocean, therefore, is not soft sediment but a continuous layer of rock constantly interacting with the water above it. This water-rock interface is a potential powerhouse of chemistry. The heat from Europa's interior, generated by the same tidal flexing that powers Io's volcanoes, though to a lesser degree, is thought to drive hydrothermal vents on the ocean floor. On Earth, such vents, called black smokers, spew superheated, mineral-rich water into the deep ocean, providing the energy and chemical building blocks for entire ecosystems that thrive in total darkness, independent of the sun. This possibility opens the door to one of the most exciting ideas in astrobiology, that Europa's ocean could be a habitat powered by chemosynthesis, where microbes derive energy from chemical reactions rather than sunlight. The water percolating through the hot rocks would leach out not just salts, but also compounds like sulfides and methane, and potentially even more complex organic molecules. The constant tidal kneading of the moon would keep this environment energetically active, preventing it from becoming a stagnant, frozen relic. The ocean's composition, therefore, might be a rich, life-giving broth, constantly refreshed and energized by its geological connection to a warm, rocky core. Yet, a major mystery persists: the pH level of this alien sea. Some models suggest that the water rock reactions on Europa's seafloor should make the ocean extremely acidic, a harsh environment that would challenge most known life forms. Other models, however, argue that the chemistry should trend in the opposite direction, producing a more alkaline ocean, similar to the conditions found around Earth's own hydrothermal vents. The true nature of this environment remains one of the key questions that future missions, like NASA Europa Clipper, are designed to investigate. By analyzing the material in the plumes that occasionally erupt from Europa's surface, we may finally get a direct taste of this hidden ocean's chemistry, determining whether it is a corrosive dead zone or a potentially nurturing cradle for life. The final piece of this compositional puzzle involves oxygen, a potential energy source that could fuel life even in the abyssal dark. Europa resides within Jupiter's ferocious radiation belts, which constantly bombard its icy surface. This radiation has enough energy to break apart water-ice molecules, creating oxygen and other oxidants. Over billions of years, a considerable amount of this surface oxygen could have become trapped in the ice. The constant churning and recycling of Europa's ice crust, where old ice sinks down and new ice rises up, could be slowly transporting these oxidants from the surface down into the ocean below. If this process occurs, it would deliver a steady rain of chemical energy into the ocean, where it could mix with the reductants coming up from the hydrothermal vents below. This would create a planet-wide gradient of energy, much like the difference between a battery's positive and negative terminals, offering a powerful and sustained fuel source for any biological processes that might have arisen in the eternal night. From the volcanic fury of Io and the subsurface ocean of Europa, we now turn to the king of Jupiter's moons, Ganymede. This isn't just another icy satellite. It's a world that defies simple classification, a moon that possesses a characteristic so rare and planetary that it stands utterly alone in our solar system. Ganymede has its own magnetic field. Of all the hundreds of moons orbiting planets in our cosmic neighborhood, Ganymede is the only one known to generate this protective magnetic bubble from within its own core, a feature that puts it in a league normally reserved for planets like Earth or Mercury. This incredible attribute immediately presents a double-layered mystery. First, how does a moon, an object typically seen as geologically dead or simple, power such a complex internal dynamo? And second, how does this relatively small, self-generated field possibly survive its daily immersion within the crushing, chaotic maelstrom of Jupiter's own magnetosphere, the largest and most powerful structure in our entire solar system? The source of Ganymede's magnetic field points directly to the Moon's surprisingly dynamic and differentiated interior. Unlike a simple ball of rock and ice, Ganymede has a complex internal structure that more closely resembles a terrestrial planet. Data from the Galileo spacecraft revealed that Ganymede is fully differentiated, meaning its interior has separated into distinct layers based on density. At its heart lies a dense metallic core, likely composed primarily of iron. Surrounding this is a rocky mantle, and encasing that is a vast shell of water ice and a global subsurface ocean. The secret to the magnetic field is believed to lie in that hot metallic core. For a magnetic field to be generated, a planet or moon requires three key ingredients: a conducting fluid, internal heat to drive convection and rotation. Scientists believe that Ganymede checks all these boxes. The heat needed to churn that molten iron core likely comes from two sources. The first is the lingering primordial heat from the Moon's formation, trapped inside for billions of years. The second, and perhaps more crucial source, is tidal heating. Although not as intense as on Io, Ganymede's orbital resonances with Europa and Io still flex its interior, providing just enough extra energy to keep the core molten and actively convecting. This churning motion of the liquid metal acts as a self-sustaining dynamo, generating the magnetic field that extends out into space around the Moon. But this is where the mystery deepens profoundly. Ganymede's personal magnetic field doesn't exist in a peaceful vacuum. It is locked in a constant, invisible battle with Jupiter's own colossal magnetosphere. Jupiter's field is titanically powerful, and it sweeps past Ganymede at tremendous speed, dragging a soup of plasma with it. Ganymede's much smaller field doesn't have the strength to hold this Jovian onslaught completely at bay. Instead, it does something astonishingly complex. It carves out a miniature magnetosphere within Jupiter's own. As Jupiter's magnetic field and plasma flow around Ganymede, the Moon's intrinsic field creates a protective cavity, a magnetic bubble around itself. At the boundary where these two fields meet and push against each other, intense currents flow, and particles are accelerated to high energies. The resulting structure has a bow shock upstream of Ganymede and a long magnetic tail downstream, a perfect miniature replica of Earth's magnetosphere interacting with the solar wind, but playing out on a much smaller scale right under Jupiter's nose. The most visually stunning consequence of this interaction is Ganymede's auroras. Just like on Earth, charged particles from the surrounding plasma are funneled by magnetic field lines down into Ganymede's thin atmosphere near its poles, causing the gases there to glow. But because Ganymede's magnetic axis is tilted relative to Jupiter's, these auroras don't just sit still at the poles, they rock back and forth. As Ganymede orbits and Jupiter's magnetic field shifts around it, the connection points for these field lines change, causing the auroral ovals to sway in a rhythmic dance. Observations of this rocking motion from the Hubble Space Telescope were in fact the key evidence that confirmed the existence of Ganymede's intrinsic magnetic field in the first place, providing a beautiful and direct window into the invisible forces battling around this distant world. This delicate and dynamic interplay makes Ganymede a unique natural laboratory, a place where we can study the complex physics of two magnetic fields in conflict, offering insights that reach far beyond our own solar system and into the interactions of exoplanets with their parent stars. While Ganymede dazzles with its self-generated magnetism and Europa intrigues with its hidden ocean, the fourth of Jupiter's great Galilean moons presents a starkly different, yet equally profound mystery. Callisto is a world frozen in time, a battered relic that looks precisely as a moon should after 4 billion years in the chaotic Jovian system. Its surface is the most heavily cratered in the entire solar system, a dark, icy landscape pockmarked by countless impacts, with no young, smooth plains or towering volcanoes to be found. This ancient face stands in shocking contrast to its violently active sibling Io and its geologically refreshed neighbors Europa and Ganymede. The central puzzle of Callisto is not about what processes are reshaping it today, but rather why, in a system defined by dynamic change and tidal forces, this large world has apparently been doing nothing for eons. Its profound geological silence speaks volumes about the formative conditions of Jupiter's miniature solar system. The key to this mystery lies in understanding the primary engine that drives geological activity on Moon's internal heat. For Io, Europa, and Ganymede, that heat comes from a powerful gravitational tug of war with Jupiter and each other. These three moons are locked in an orbital dance known as a Laplace resonance. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This perfect repeating rhythm means their gravitational pulls constantly tug on one another, preventing their orbits from becoming perfectly circular. This slight orbital eccentricity causes Jupiter's immense gravity to flex and stress their interiors in a process called tidal heating, which melts rock, maintains subsurface oceans, and drives world-altering geology. Callisto, however, is the odd moon out. It does not participate in this resonant dance. Its orbit lies farther out, beyond the gravitational reach of this precise clockwork, and is much more circular as a result. Without that constant, rhythmic flexing from its neighbors and Jupiter, Callisto's interior experiences far less tidal heating, leaving it a much colder and more geologically stagnant world. But this explanation only deepens the mystery. Why is Callisto not part of the resonance? Its current, quiet orbit is a clue to its origin story, and it tells a tale that challenges our standard model of how the Galilean moons formed. The leading theory, known as the accretion disk model, suggests all 4 large moons formed from a swirling disk of gas and dust that surrounded the infant Jupiter. In this scenario, the moons would have formed relatively quickly, close to the planet, and their orbits would have migrated outward over time due to gravitational interactions with the disk, eventually locking the inner 3 into their resonant configuration. Callisto's distant and unresonant orbit suggests it may have formed much later than the others, after this primordial gas disk had already dissipated, preventing it from migrating inward and joining the gravitational dance. Alternatively, it may have formed farther out in the disk where material was more sparse, accreting slower and never quite reaching the mass or proximity needed to be pulled into the orbital resonance that so dramatically shaped its siblings. This makes Callisto a priceless time capsule. Its undisturbed surface is a direct record of the earliest, most violent period of our solar system, the late heavy bombardment, when countless asteroids and comets rained down on young worlds. On Earth, plate tectonics and erosion have erased this ancient history. On the Moon, vast lava flows from later volcanic activity buried much of the evidence. But on Callisto, the record remains perfectly preserved in ice. Every crater, from the tiny to the basin-sized, tells a story of an impact that happened billions of years ago. By studying this frozen archive, we can calibrate the entire timeline of impacts across the solar system, using Callisto as a stable reference point to understand the bombardment history of every other terrestrial world. The most tantalizing discovery from spacecraft like Galileo, however, is that Callisto might not be entirely dead. Precise measurements of its gravitational field suggest that beneath this ancient cratered shell of ice and rock, there might lie a hidden liquid water ocean. This is perhaps the ultimate twist in the mystery. How can a moon with insufficient tidal heating to power volcanoes or resurface its exterior still maintain a vast subsurface ocean? The answer likely lies in a combination of factors. The internal heat left over from its formation, trapped by the insulating properties of its thick, icy crust, could still be slowly leaking out. Furthermore, antifreeze compounds like ammonia dissolved in the water could significantly depress its freezing point, allowing it to remain liquid at much colder temperatures than pure water. This possibility transforms our view of Callisto from a simple, frozen relic into a potential stealth ocean world, proving that geological activity and habitability can emerge from quiet, cold patience just as they can from violent tidal fury. Its silent surface, therefore, is not a sign of a barren world, but a mask hiding its own deep, slow secrets. But to truly understand the scale of this puzzle, we must shift our gaze from the individual features of Jupiter and its moons to the planet's most profound role of all, that of a master architect. For decades, we've viewed our solar system structure as a settled matter, with rocky worlds close to the sun and gas giants orbiting farther out. But what if this orderly arrangement is merely the end result of a violent, chaotic construction process, a celestial drama in which Jupiter played the lead role? The emerging and deeply compelling mystery is that Jupiter may not have formed in its current orbit at all. Instead, it might have gone on a colossal journey across the early solar system, a migration that would have utterly reshaped the entire cosmic neighborhood, scattering building blocks, destroying nascent worlds, and ultimately determining the very size and nature of our own planet Earth. This revolutionary idea is known as the Grand Tack hypothesis. The name comes from the sailing term tack, meaning to change direction. The theory proposes that in its infancy, Jupiter began to form at a distance of about 3.5 astronomical units from the Sun, roughly where the asteroid belt is today. As it grew, its immense gravity began to interact with the vast disk of gas and dust from which the planets were forming. This interaction created a drag, causing the young planet to slowly spiral inward toward the Sun. This inward migration, if left unchecked, would have sent Jupiter careening into the inner solar system, likely gobbling up or ejecting the protoplanets that would become Mercury, Venus, Earth, and Mars. Our home might never have had a chance to form, but just as this disaster seemed inevitable, Saturn finally coalesced further out. As Saturn grew, its own gravity locked into a specific orbital resonance with Jupiter. This gravitational link acted like a cosmic leash, pulling Jupiter back outward and causing both giants to migrate away from the Sun until they settled into their current orbits. This tacking maneuver inward, then outward, would have dramatically sculpted the inner solar system, potentially explaining why the terrestrial planets are both small and relatively short on mass compared to the giants. The evidence for this grand migration is written in the stars, or more precisely, in the asteroids. The main asteroid belt between Mars and Jupiter is not a dense, continuous ring of rock as often depicted in films. It is mostly empty space with a total mass of all its objects amounting to less than that of our Moon. More curiously, the belt is not uniform. It contains a wild mix of two very different types of material: dry, rocky S-type asteroids closer to Mars and carbon-rich, primitive C-type asteroids farther out. The Grand Tack model elegantly explains this jumble. As Jupiter marched inward on its initial migration, its gravity would have scattered the original population of the inner asteroid belt, sending most of its material flying. Then, on its outward tack, it would have dragged in a new population of primitive, water-rich asteroids from the outer solar system, depositing them in the belt and creating the mixed constituency we see today. This single event could have been the delivery mechanism that brought water and organic materials to the inner solar system, seeding the young Earth with the essential ingredients for life. Yet, not all scientists are convinced by this grand narrative. Competing models suggest a more sedate formation history, where Jupiter formed more or less in place through a process known as pebble accretion. This theory posits that the planet grew rapidly by gravitationally attracting countless centimeter-sized pebbles of ice and rock drifting in from the outer disk. This model can explain Jupiter's rapid growth and potentially its fuzzy core without requiring a large-scale migration. The debate between these two ideas, the dynamic grand tack and the more local pebble accretion, is fierce because the implications are monumental. Each theory predicts a very different composition for Jupiter itself. If it migrated significantly, it should have accreted material from a wide range of locations in the protoplanetary disk. If it formed mostly in place, its composition should more closely reflect the conditions at its current orbital distance. This is where the Juno mission's measurements of Jupiter's water and heavy element abundance become absolutely critical. The planet's composition is a frozen record of the building materials available where and when it formed, the preliminary data suggesting a possible depletion of water, even if localized, has thrown a wrench into all the models. A widely migrating Jupiter should have a very rich abundance of heavier elements, while a Jupiter that formed in place might be leaner. The data we have so far doesn't neatly fit either prediction perfectly, indicating that our understanding of the early solar system's composition and the physics of planet formation is still incomplete. Jupiter's true origin story remains locked inside its own atmosphere, a secret it has kept for over 4 billion years. Unraveling it is not just about understanding one world, it is about rewriting the Genesis story of our entire cosmic home, and learning whether our existence is the product of a serene, orderly process, or the spectacularly fortunate outcome of a gravitational roller coaster ride led by the solar system's largest and most influential planet. Surrounding the familiar, orderly dance of the 4 large Galilean moons lies a far stranger and more chaotic family, a scattered collection of nearly 80 smaller bodies known as the irregular moons. Unlike their massive siblings which orbit neatly around Jupiter's equator, these moons are the cosmic rebels. They follow wildly eccentric, tilted paths, often moving in the opposite direction of Jupiter's rotation, and they are scattered so far from the planet that their gravitational allegiance is a constant tug of war between Jupiter and the Sun. Their very existence is a monumental puzzle, presenting us with a fundamental question of planetary archaeology. How did Jupiter, a planet with gravity so strong it can shape the entire solar system, come to acquire such a disordered and motley crew of celestial hitchhikers? The most immediate clue to their origin lies in their orbits. The irregular moons are not a unified group. They are starkly divided into families based on the inclination and direction of their paths. Some, known as the prograde moons, orbit in the same direction as Jupiter's spin, though their orbits are still highly tilted and elliptical. Others, the retrograde moons, boldly orbit in the exact opposite direction. This dramatic division is a classic signature of capture. These moons did not form alongside Jupiter in the primordial circumplanetary disk that gave birth to Io, Europa, Ganymede, and Callisto. Instead, they are almost certainly captured asteroids, wandering nomads from the outer reaches of the solar system that were somehow snared by Jupiter's immense gravity and persuaded to stay. But this simple answer only opens the door to a far more complex mechanical mystery. How do you capture an asteroid? Capturing a free-flying object into a stable planetary orbit is one of the most difficult tricks in celestial mechanics. An object falling toward a planet from a great distance will gain speed, whip around it, and unless something slows it down, will escape with the same energy it arrived with, continuing on its way. It's a gravitational slingshot, not a trap. For capture to occur, the incoming asteroid must lose a significant amount of its orbital energy. So what cosmic break could possibly slow down a speeding asteroid enough for Jupiter to grab it and hold on? For a long time, the leading theory involved gas drag. In the very early solar system, Jupiter was still embedded within its own expansive circumplanetary disk of gas and dust. An asteroid passing through this thick, primordial atmosphere would have experienced friction, slowing down just enough to lose its escape velocity and become trapped in a new orbit around the planet. This elegant solution, however, has a major flaw. It only works for prograde capture, where the moon is moving in the same direction as the rotating gas disk. It cannot explain the existence of the large population of retrograde moons. To solve that part of the puzzle, scientists had to consider a far more violent and chaotic scenario involving not two bodies but three. The most promising explanation for the capture of the retrograde moons is the gas drag theory's more dynamic cousin, gravitational interaction within a swarm of objects. Imagine the early solar system not as a tidy place with well-separated planets, but as a crowded shooting gallery filled with thousands of protoplanets and asteroids. In this environment, an asteroid could be captured through a complex gravitational dance with other bodies. If a small asteroid were to make a close pass by a larger one just as they were both swinging by Jupiter, the smaller one could transfer some of its kinetic energy to the larger one. The larger asteroid would be flung away with even greater speed, while the smaller one, now slowed down, would fall into a bound orbit around Jupiter. This three-body interaction provides a viable mechanism for capture that works for both prograde and retrograde orbits, painting a picture of a young solar system where such chaotic exchanges were commonplace. Yet the plot thickens when we look at the moons themselves. If these are captured asteroids, we would expect their compositions to broadly match those of asteroids we find in the main belt between Mars and Jupiter, or perhaps those from the more distant Trojan swarms that lead and follow Jupiter in its orbit. But spectroscopic studies reveal something curious. Many of Jupiter's irregular moons are far darker and redder than most asteroids, with surfaces that suggest a composition rich in complex organic compounds, more akin to the primitive bodies found in the distant Kuiper belt or among the centaurs that wander between the giant planets. This creates a fascinating contradiction. The capture mechanisms that seem most plausible gas drag or three-body interactions would have been most effective in the early, crowded inner solar system, closer to where the main belt asteroids reside. But the composition of the moons suggests they originated much farther out, in the cold, dark frontier beyond Neptune. So how did these seemingly foreign objects from the outer solar system get close enough to Jupiter to be captured? This discrepancy points toward an even grander narrative of solar system evolution. It's possible that the capture of these distant objects was not a localized event around Jupiter, but a consequence of a massive planetary migration that reshaped the entire outer solar system. The most prominent model, known as the Nice model, suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. After the dispersal of the primordial gas disk, gravitational interactions between these giants and a vast surrounding disk of leftover icy planetesimals caused their orbits to become unstable and shift. As the planets migrated, they would have violently scattered countless of these icy bodies inward from the trans-Neptunian region. A fraction of these scattered invaders, thrown into the realm of the giant planets, could have been captured during close encounters, becoming the irregular moons we see today. In this light, Jupiter's irregular moons are not local captives, but refugees from a cosmic upheaval, the last survivors of a population of ancient icy bodies that were scattered across the solar system during its most dynamic and violent era. Their dark, red surfaces are a testament to their primordial origins in the deep freeze of the solar system's outskirts, and their chaotic orbits are the permanent scars from the gravitational turmoil that delivered them to their unlikely home. While the chaotic orbits of Jupiter's irregular moons tell a story of capture and cosmic upheaval, our next mystery brings us back to the planet itself, to a phenomenon that unfolds not over millennia but over decades, visible to any dedicated observer with a telescope. We've already seen how Jupiter's belts and zones can change color in a relatively short time, but this is just one piece of a much larger and more baffling puzzle. The entire Jovian atmosphere seems to be undergoing a series of mysterious, long-term cycles that defy our attempts to model and predict them. This isn't about the daily churn of storms, it's about planetary-scale transformations that play out on a human timescale, a slow-motion symphony of change whose conductor remains completely unknown. The most dramatic of these changes is the occasional and complete disappearance of one of Jupiter's iconic dark belts. The most famous example is the South Equatorial Belt, a prominent band that has vanished from view entirely on multiple occasions, most recently in 2010. To an amateur astronomer, the effect is shocking. One of the planet's most recognizable features simply fades away, leaving a vast, blank white zone in its place. The prevailing explanation is that brilliant, high-altitude ammonia ice clouds form in the region, effectively obscuring the darker, warmer material of the belt beneath. But this only raises a more fundamental question. What triggers the sudden, planet-wide uprising of these bright clouds in one specific latitude? And why does it happen so irregularly, sometimes remaining absent for months or even years before the dark belt suddenly and violently erupts back into view? These grand transformations extend beyond mere color shifts. The entire jet stream system that defines Jupiter's banded appearance appears to be subject to long-period variability. Historical records and modern measurements suggest the speeds and widths of these colossal rivers of air are not constant. They can slow down, speed up, and even slightly shift their positions over time. Furthermore, the planet's global temperature seems to fluctuate in ways that are uncorrelated with the Sun's 11-year activity cycle, indicating that an internal heat source, not external sunlight, is the primary driver of these changes. The atmosphere behaves as a coupled system, where a change in one part can ripple around the globe, causing unexpected effects in another. A storm erupting at the equator might influence the polar temperatures years later, a delayed reaction we are only beginning to trace through decades of patient observation. So what is the ultimate engine behind these slow, rhythmic pulses? The prime suspect is Jupiter's incredible internal heat flow. The planet's interior is a churning cauldron of energy, and the rate at which this heat escapes into the atmosphere is unlikely to be perfectly steady. It may come in great, sluggish waves or pulses. Imagine a pot of water on a stove. Just before it boils, you'll see large bubbles of vapor form at the bottom, rise, and release their energy at the surface. On a planetary scale, these could be massive bubbles of warm, moist material called planetary waves that take decades to brew in the deep interior before finally buoying up to the visible cloud layers, where they radically alter the climate for a period before dissipating. This would make Jupiter's long-term cycles a direct window into the otherwise invisible convection patterns of its deep interior. However, an intriguing alternative theory looks not inward but outward toward the Sun. While Jupiter's own heat dominates its weather, the Sun's output is not insignificant, particularly in the form of ultraviolet radiation. This high-energy light doesn't penetrate deep into the atmosphere, but it does have a powerful effect on the chemistry of the very uppermost cloud layers. It can break apart molecules, creating the complex compounds that act as chromophores and darken the belts. A slight variation in the Sun's UV output over a multi-decadal cycle could therefore act as a trigger, initiating a chemical chain reaction that alters cloud color and, by changing how much sunlight is absorbed, could eventually influence the deeper atmospheric dynamics. The planet's own internal rhythms might then be modulated or kicked into a new state by these external nudges from the Sun. The greatest challenge in solving this mystery is time itself. Jupiter's year lasts 12 of our own, and some of these proposed cycles may operate on centennial or even longer timescales. Our detailed spacecraft quality data only covers a mere 50 years, a single snapshot in the life of a 4.5 billion-year-old planet. We are like a visitor who arrives at Earth for 5 minutes and tries to understand the intricacies of the Ice Age cycle. Each new decade of observation adds another crucial data point, bringing us closer to understanding whether we are witnessing random fluctuations or the steady, predictable heartbeat of a giant, a rhythm set by the slow and powerful circulation of its deep, hidden heart. After exploring the grand, slow cycles that may pulse through Jupiter's atmosphere, We now turn to a mystery that requires us to look at the planet's very essence, its atomic building blocks. When we measure the composition of the Sun, we get a standard cosmic recipe, a baseline for the relative abundances of elements that formed from the same primordial cloud of gas and dust that birthed the entire solar system. We expect giant planets like Jupiter, which gathered their material from this same reservoir, to largely mirror this recipe, but they don't. Jupiter's atmosphere holds unexpected and puzzling deficits and surpluses of certain elements, and the most baffling discrepancies of all involve a group of elements that are famously aloof and unreactive, the noble gases. The way argon, krypton, and xenon are distributed within the giant planet presents a profound contradiction that strikes at the heart of our models for how such worlds are born. The noble gases are the hermits of the periodic table. They don't readily form chemical compounds or condense into ices. This means that during planetary formation, their behavior is governed almost entirely by temperature. They don't get selectively locked away in rocky minerals or icy grains. So, if a planet formed directly from the solar nebula, we would predict its noble gas abundances to perfectly match the Sun's, as these inert elements would have been easily scooped up along with the hydrogen and helium. This is why the Galileo probe carried a special instrument designed to measure them directly when it plunged into Jupiter's atmosphere. The results were startling. While some noble gases like helium and neon were found in roughly solar proportions, the heavier ones argon, krypton, and xenon were all significantly enriched compared to solar abundance. They were up to 3 times more common relative to hydrogen than they are in the Sun. This was completely unexpected. If Jupiter formed from a well-mixed soup of nebular gas, all these elements should be present in their pristine solar ratios. Their enrichment means that the material that built Jupiter was not the nebula gas alone. Something else, something carrying an extra helping of these heavy noble gases, must have been added to the mix. This discovery immediately pointed a finger at a different type of building block: solid planetesimals, the icy and rocky chunks that populated the early solar system. The leading theory to explain the enrichment is that these heavier noble gases weren't delivered as free gas, but were instead trapped inside ice crystals in the frigid outer solar system. A process called clathration could have imprisoned atoms of argon, krypton, and xenon within cage-like structures of water ice at very low temperatures. As these icy planetesimals were later accreted by the growing Jupiter, they would have released their trapped noble gas cargo, enriching the planet's atmosphere beyond what could be accounted for by gas capture alone. This suggests that solid objects played a much more significant role in building Jupiter's bulk than the traditional core accretion model assumed, with planetesimals contributing a substantial fraction of the heavy elements. However, this elegant solution is complicated by the behavior of another noble gas, neon. The Galileo probe found that neon, in stark contrast to its heavier cousins, was actually depleted in Jupiter's atmosphere. It was less abundant relative to hydrogen than it is in the Sun. This is where the plot gets even thicker. Neon's behavior can be explained by a process called helium rain. Deep in Jupiter's interior, where pressures are immense, it's theorized that helium can become insoluble in liquid metallic hydrogen and form droplets. As these droplets rain down toward the planet's core, they can drag dissolved neon atoms down with them, effectively depleting neon from the upper atmosphere where we can measure it. This creates a bizarre situation where one noble gas is being dragged down out of sight, while others are apparently being enriched from below or from delivered solids. The real conflict arises when we try to reconcile these measurements with competing planetary formation theories. The core accretion model, which has been the standard for decades, posits that Jupiter first formed a massive rocky icy core of about 10 Earth masses, which then triggered a rapid accretion of surrounding nebula gas. In this model, the noble gas enrichment from planetesimals makes sense. However, an alternative model, known as pebble accretion, suggests Jupiter could have formed very rapidly by gobbling up countless centimeter-sized pebbles of ice and rock directly from the solar nebula. This model has gained traction because it can explain Jupiter's rapid formation and its fuzzy, diluted core, but it also predicts a different outcome for noble gases. If pebble accretion dominated, the planet's composition should more closely reflect the particular region of the nebula where it formed, potentially with less overall enrichment from a specific population of solid planetesimals. The fact that we see such clear and significant enrichments in heavy noble gases poses a serious challenge to the purest versions of the pebble accretion idea, forcing its proponents to find ways to incorporate more solid delivery into the process. This leaves us with a deeply intriguing puzzle. The noble gases are acting as independent, unbiased witnesses to Jupiter's formation, but their testimony is complex and in some places contradictory. The enrichment of argon, krypton, and xenon screams that solid delivery was crucial, while the depletion of neon whispers a story of complex interior processes that are still ongoing billions of years later. Unraveling this requires us to view Jupiter not as a static entity, but as a dynamic system that was built in one way and has been evolving in another ever since. The precise ratios of these inert elements are a frozen record of the planet's earliest days, a chemical signature that has survived intact for over 4 billion years. Decoding it fully will require not just more atmospheric probes, but a better understanding of the exotic physics happening in the planet's deep interior, where the fate of elements like neon is ultimately decided. This atomic-level mystery reminds us that the grandest questions about planetary birth are often answered by studying the smallest and most reticent of clues. After exploring how Jupiter's composition holds secrets to its formation, we arrive at a mystery not of chemistry but of sound, a symphony of radio waves broadcast by the planet itself. For our final enigma, we turn to Jupiter's strange radio emissions, powerful bursts of energy that have baffled astronomers since their chance discovery in 1955. Unlike the steady thermal radio waves given off by all warm objects, these are non-thermal, sporadic, and immensely powerful shrieks and whistles in the decametric band, wavelengths tens of meters long. They were the first definitive proof that Jupiter was not a placid, silent world, but an intensely active and dynamic one, a radio lighthouse whose beacon flashes with a signal we are still struggling to fully decode. The initial clue to this puzzle was almost as strange as the emissions themselves. Their timing is curiously tied to the orbital dance of the volcanic moon Io. Observations revealed that these radio bursts are far more likely to occur when Io is at certain positions in its orbit around Jupiter, particularly when it is either at its farthest point from the planet in its elliptical path or when it is moving toward or away from Earth in its orbit. This strong correlation immediately suggested that Io is not a silent partner. It is an active participant, somehow triggering these colossal bursts of energy. The moon's constant volcanic eruptions spew tons of ionized gas, primarily sulfur and oxygen, into space, which becomes trapped by Jupiter's powerful magnetic field. This creates a vast, donut-shaped plasma torus that follows Io's orbit, a ring of supercharged particles that acts as a ready reservoir of fuel for Jupiter's radio engine. But how does this plasma torus actually generate the radio waves? The leading theory involves an immense and invisible electrical circuit connecting Io to Jupiter's poles. As Io and its plasma torus plow through Jupiter's magnetic field at supersonic speeds, they generate a powerful electrical current, millions of amps flowing along magnetic field lines. This current, called the Io flux tube, acts like a giant natural generator. Scientists believe that this flow of charged particles can become unstable, leading to a phenomenon known as the cyclotron maser instability. In this process, electrons are accelerated to high energies and forced to spiral along Jupiter's powerful magnetic field lines. As they spiral, they release their energy not as light or heat, but as coherent, intense beams of radio waves, much like the beam from a laser but at radio frequencies. This beam is then broadcast into space, and when it sweeps past Earth, our radio telescopes detect it as a brief, powerful burst. However, this elegant explanation is far from complete. The precise mechanisms within this process remain hotly debated. For instance, why do these emissions occur so sporadically? If the EO interaction is constant, why isn't the radio emission constant? The answer likely lies in the complex and often chaotic nature of the plasma itself. The transfer of energy may require very specific thresholds to be met, a certain density of particles in the torus, or a particular alignment of magnetic field lines, before it can cascade into the explosive release of a radio burst. It's akin to building up pressure behind a dam. The water is always there, but the release only happens when the gate is opened. Furthermore, the emissions are strongly beamed, meaning we only hear them when Jupiter's rotating magnetic field points the radio beam directly at Earth, adding another layer of chance to our observations. The most baffling aspect of these radio shrieks is their specific frequency. The cyclotron maser theory predicts that the frequency of the emission should be directly tied to the strength of Jupiter's magnetic field and the mass of the electron, a value known as the electron-cyclotron frequency. Yet, the observed emissions often occur at frequencies that are slightly off from this predicted value, or they exhibit complex fine structure, multiple frequencies close together, suggesting a far more intricate and poorly understood process is at work. Some researchers propose that the presence of different ions in the plasma, not just electrons from hydrogen, but heavier ions from EO like sulfur and oxygen, could be modifying the emission in ways our current models don't account for. It's also possible that the emissions are generated not in a single, neat location, but in multiple, cascading regions along the magnetic flux tube, each adding its own signature to the final signal we receive. This mysterious radio broadcast is more than just a Jovian curiosity. It provides a powerful remote sensing tool, because the frequency of the emission is directly influenced by the strength of the magnetic field at its point of origin. Astronomers can use these radio bursts to map the structure of Jupiter's magnetic field in regions far from the planet, especially near Eo's orbit. Every burst is a probe, sending us information about the invisible magnetic forces shaping the space around the giant planet. Furthermore, understanding this process is crucial for our exploration of the universe beyond our solar system. Many exoplanets we have discovered are gas giants, and if they possess strong magnetic fields and interacting moons, they too might be broadcasting similar radio shouts into the cosmos. Learning to interpret Jupiter's complex radio song may one day provide us with the key to hearing the hidden voices of distant worlds, turning the silent points of light in our telescopes into dynamic, speaking planets with stories of their own to tell. From the churning, storm-racked cloud tops to the enigmatic depths of its exotic interior, Jupiter stands as a monumental testament to the awe and mystery that defines our solar system. We've journeyed through 25 profound enigmas, each one peeling back a layer of this giant world to reveal a deeper, more complex reality than we ever imagined. The Great Red Spot's ancient fury, the planet's bafflingly fuzzy core, the chaotic symphony of its magnetic field, the hidden water and segregated ammonia, all of these puzzles converge on a single, humbling truth. Jupiter is a world that constantly defies our textbooks and forces us to rewrite the cosmic rules. Consider the implications of what we don't know. This isn't just about one planet, it's about a fundamental pillar of planetary science. Jupiter is the archetype, the prime example of a gas giant. If we misunderstand its formation, its inner workings, and its evolution, then our entire framework for understanding the thousands of giant exoplanets orbiting other stars is built on a shaky foundation. Each mystery, from the geometric perfection of the polar cyclones to the silent, ancient surface of Callisto, serves as a crucial data point in a model that is still very much under construction. The planet's radio shrieks, its missing mid-size moons, and its long-term climate cycles are not mere curiosities. They are vital clues in a 4.5 billion-year-old story that we are only now beginning to read. This grand journey of discovery is far from over. Every unanswered question is an invitation, a beckoning path for the next generation of explorers, both robotic and human. Missions like Europa Clipper will soon give us our first taste of an alien ocean, while future probes may one day dive into the clouds themselves. The greatest lesson Jupiter teaches us is one of profound humility and boundless curiosity. It reminds us that the universe is always more inventive, more violent, and more wonderful than our boldest theories, so we want to hear from you. Which of these 25 mysteries captures your imagination the most? Is it the potential for life in Europa's dark sea, the relentless volcanic rage of Io, or the haunting possibility that Jupiter's migration once made our own existence possible? Share your thoughts in the comments below, and never stop looking up and wondering about the incredible wonders waiting in our own cosmos.